I hope you did your reading last night, because now we're going to get into the nitty-gritty details. Okay, to make life a bit easier, we're going to go off and recycle the stuff that we learned from gravity and reapply it into the world of into the electric universe, all right? Because since the equations are so similar, we can recycle the same formatting and just change certain letters around so that it works in the universe of energy. All right. First off, if you recall these equations from gravity, work is equal to force times distance, and the force acting on an object is equal to the mass of the object times the gravitational field strength acting on the object. In the world of electric potential energy, remember, these both are realms of energy. So the first formula is still the same. Work is still equal to force times distance. However, the second formula will be slightly different. All right. The electric force acting on a charge is equal to the charge multiplied by the electric field itself. All right. So if you double the charge, then the force acting on the charge will be double. Just like if the mass is double, then the force of gravity acting on the object will be double as well. So that's a direct correlation. Those are fairly straightforward. With regards to work, if it's a work involved in moving an object from here to here, if we assume that g is equal to 9.81 down here, and it's still equal to 9.81 over here, which is still the same as 9.81 all the way up over there, then yeah, we can use this shortcut lazy formula. All right, that formula works if g is constant. There's a synonymous one for the world of energy. If we assume the electric field is constant in the same value, then the work required in moving a charge from point A to point B is equal to a very similar structure. Instead of M, we have Q. Instead of G, we have E, just like before. Okay, and the distance, well, this is a height, and from point A to point B, we'll just call it delta D. That's all. So it's just a measurement of distance between these two. Okay, so the formulas are still fairly similar, just different variables are used instead. That's all. All right, but very similar structure. So if this is the work required to move an object from point A to B in elevation height, now the object has a certain amount of energy stored in it. All right, so this is the gravitational potential energy stored based upon this. Just like the electric potential energy stored when you pass a charge through a certain field in a certain distance. Remember that whole elastic band thing I was talking about? Now that charge has a certain amount of energy stored in it, and that energy can be released if you let go of that charge. Okay, so these formulas work perfectly fine in a universe where G or E is constant. All right, if it's not constant, then things get messy. And as you may know, gravity is not consistent, or the force of gravity is not consistent. All right, the gravitational field strength down here might be at 9.81, but somewhere up here it'll be at 9.80, and somewhere even higher will be at 9.79, and so on and so forth. All right, so the force acting on a charge does decrease over distance, and that's governed by Newton's universal law of gravity equation. Okay, where he once stated before he died that the force acting between two objects is equal to the product of the masses divided by the distance of separation squared, and yeah, you multiply it by some unknown constant. Unfortunately, he died before he could figure out what it was. He knew it was a very small value. Today we know it's 6.67 times 10 to the negative 11. That's why it's so small. And then that's the constant there. Okay, and in the world of E fields, the same thing is also true. Okay, if you place charges further and further apart, the amount of attraction or repulsion will be weaker the further you move it away. It's kind of like magnets as well, right? You put magnets really close together, the force of attraction or repulsion is really strong. You place them farther away, and the intensity is not as strong. The only difference is that with regards to magnetism, it's not an inverse squared correlation. I believe it's an inverse cubed correlation. Okay, but we don't need to worry about it in high school, right? It's a university topic. But for our purposes here are the formulas that we've covered earlier. You can see how similar the structure of them are. Now, another thing that is going to be similar is trying to figure out the area underneath the curve. And if you recall, by definition, work is the area underneath the force distance graph. All right, and to solve this, the best way to do it is to perform the integral of these equations, as the integral is solving for the area underneath the curve. And that's what I want to get to right now, all right? Because an inverse squared correlation, if you do the integral of it, if you recall, it's equal to negative r to the negative 1. Okay, that's the integral of 1 over r squared. All right, so the if you do the integral of this formula over here, it will work out to this over here. Okay, and you can repeat the same thing with regards to charges. If you do the integral of this with respect to radius, you get a very similar looking formula. Only difference now is now you have to think about plus or minus. With regards to gravity, it's always a force of attraction. Okay, always. And in that force of attraction, when you do the integral, you end up creating a minus sign for attraction. Meanwhile, with charges, well, there's another case that can occur, right? Because if you have two like charges, they will repel. So in the first case, if they repel, then you know that the integral of this will be positive, and if they attract, then the integral will be minus. All right, so there is going to be this plus minus discrepancy, and you have to really think about the two charges. All right, because if they're like charges, they will repel, and if they're unlike charges, they'll behave just like gravity and attract. And as a result, when you do the integral, it will have a negative integral. Okay, so yeah, that you have to keep in mind. As a visual diagram of the E field, I think I have that listed over here. This is what it'll look like. Okay, and to finish off, this is just an expansion. All right, if you recall, by definition, work is the change in kinetic energy, and if you want to talk about the change in electric energy, then W is equal to delta U. All right, which is going to be equal to the difference of these in these two states. Okay, so we're going to use a very similar structure in solving these problems as we did at the beginning of this unit, except with gravity. Now we're dealing with electric forces and electric fields. Okay, so something I want you to add to the previous day's notes, okay, because we just want to take a formula and tweak it a little bit. We first covered this formula over here. By definition, a volt is equal to how much energy there is per unit charge. Well, if we just learned this formula just now from right down over here, okay, if we just learn this formula over here, well, we can manipulate this so it looks the same. Remember, U is energy, okay? So if we take our QT and we bring it all the way down here, then we have UE over QT, which is the definition of a volt, okay? So we bring this down over here, we can actually create a brand new formula, which looks like this. Okay, so what is a volt? Well, a volt can also be defined by the K constant multiplied by the charge of the master reference charge divided by how far away you are from it. Okay, and that's how you can determine the volt as well. Okay, how much potential work it can do based upon how many coulombs of charge that you have. Okay, remember that work can be accomplished if you are able to make an object move from point A all the way to point B. That's when you can do work. Okay, that's when we can talk about the potential difference. Okay, where we're going to take an object from point A, and if we can relocate it to point B, now we've done work. Now we can do work on an individual charge, which will be work measured in joules, or we could reference it to the work done per quantity of electrons, which will be the definition of a volt. All right, and that's where volt comes from. A volt is how much work is done per subset of electrons. There you go. Work was done just here. We covered this last day. By definition, electron volt is how much work is done in moving a charge from point A to point B within a 1 volt field. It also is a very small measurement of energy. All right, so 1 electron volt is a minuscule amount measured in joules. Okay, law of superposition, which simply states that whenever you have vectors and they are superimposed on top of each other, you create a new vector map. All right, and the new vector map is based upon the sum of the vectors that were superimposed on top of each other. Okay, so let's say that we have these two charges placed in close proximity with each other. You can see that one is positive and one is negative. So between these two, as you may recall, if the vectors are going the same direction, their intensity will intensify much more. As for up here, we're dealing with an E field that looks like this and another E field that looks like that. If we look at the vector sum of these two, you'll have a vector that looks like that, but it'll be placed right over here. Okay, or in this case over here, it's going to look like a tilt like this. And you can rinse and repeat and draw these over and over again and try to draw the resulting vector. And at the end of the day, you're going to end up with something like this. Okay, so this is the resulting vector field when you've sat down and you've done all the calculations. You can also do this with regards to like charges. As we mentioned before, if they're like charges and they're equal and opposite, these two mathematically will null each other out. So you're going to have a charge of 0 newtons per coulomb at the exact center of these. And if you do the calculations of, I guess, this vector here plus this vector over here, you'll notice that they have a sum of vertical component, but the horizontal component goes to 0. Okay, so you end up creating this asymptote-looking figure, which I'll just show you the animation. It'll just look something like that. Okay, and yeah, you could use the E-field simulator if I can activate it. Where's my mouse? Come on. It doesn't like doing that arrow. Okay, you can go and pull out the E-field simulator and show this stuff over here. You probably want to turn on the grid, and if you want a more consistent E-field map, just do direction only. So let's just resimulate what we've seen earlier. If you have two opposite charges, then you'd expect a field that looks like this. All right. I guess if you really want to see what happens in the middle, then I can just shift this down here, and you can see that they superimpose and add upon each other over here. Okay. And then I just want to bring them closer just so that you could see. Actually, it works best over here. Okay. That this picture over here looks very similar to this picture here. Okay. And if we want to have two like charges, if you're wondering how do you delete, just bring it back into the control bar here, and that's how you can delete it. If you have two like charges, you can see that there's a lot of repulsion right over here, and then this E-field map looks very similar to this E-field map over here. Okay, so you don't need to copy this down, but that's just reminding us what the corresponding field will look like when you superimpose them on top of each other. Okay, so let's go through some practice problems using the new learned vocabulary. All right, so you have three charges over here. I guess I'll label it here. Q1 is at 6 microcoulombs positive. Q2 and Q3 are at -3 and -3 microcoulombs. Okay, so that's what we're dealing with right over here. First thing we want to find out is what is the electric potential at Q1, Q2. So X marks the spot right over here. Okay, so we want to see, you know, how much or how many joules per how many electrons we put in there, how much energy there is in causing it to move from point A to point B. Okay, and it's going to be a superposition of the other fields. You have Q1, which I believe was positive, so it will be pointing downwards like so. Q2, which will be pointing like this, and Q3 was a negative charge, so all of them will be pointing like so, but we're referencing it with regards to X, so we're looking at this component pointing towards it. Okay, so we want to look at the vector sum of that, and we want to find out what the volt is at that point over there. Okay, remember that if you see E is for electric potential energy, but electric potential is the volt, so we want to look at the voltages here, and volts are measured in joules per coulomb, so we're measuring probably E over Q. Okay, and that's what we want to do. Okay, so we got to do a little bit of preliminary work because we got to first figure out what is the distance between Q3 and X marks the spot. As for the other two, it's fairly easy to solve because if the total length is 3 meters, then this is 1.5 meters here, and down here is also 1.5 meters. But this longer distance over here is going to be quite a bit more. So how are we going to solve that? Well, for one thing, you'll notice that this does create a perfect right triangle. Okay, and with right triangles, we know that the angle on each of them, well, before we drew the red line, they're all 60 degrees. Okay, so 60 degrees here, and yes, it is 30 degrees over here, but we're not going to use that number there because we don't really have to. Okay, we want the 60 degrees there because we know that the distance, at least on this side over here, is equal to, and which works out to be the hypotenuse, is equal to 3.0 meters. So we want to find out how long the opposite side is. So we have 60 degrees, we have a hypotenuse, and we're looking for the opposite side. All right, and we know that the opposite side is equal to the 3.0 meters times the sine of 60 degrees as its opposite, and that'll get us the answer. I mean, if you want to do it the longer way, you could, okay, just by knowing that sine of theta is equal, or sine of 60 degrees is equal to R34, which is the opposite side over the hypotenuse. Crunch everything in, and you will get to an answer, all right? 30 meters times the sine of 60 degrees, which is also equal to root 3 over 2 if you've learned that in math class already, which I think you should have by now. If not, it's just a decimal answer that will be on your calculator, and that's perfectly fine as well. Okay, so now that we've done our preliminary homework and we know that this is 3 meters times root 3 over 2, and these are both 1.5 meters, 1.5 meters. Now let's just do the vector sum of what's happening over here. Now you may think that, oh, now we have to go off and solve everything by component method, but just to point out something, energy is a scalar quantity. Voltage, therefore, also has to be a scalar quantity as well, because the volt, by definition, is how much energy there is per quantity of electrons. That's all it is. All right, it's just a ratio. How much energy there is per 1 electron, or how much energy there is per coulomb of electrons. Okay, which is 6.24 times 10 to the 18 electrons. Just a lot of electrons. Okay. So it's a scalar quantity. We don't need to break down things into its components. We just needed to know the radial distance, and that's why you had to do this extra homework here. Okay. And yeah, that's what we need to keep in mind there. Okay, so we're trying to look at the sum of all the voltages for that point right over here, and that's equal to KQ over R for all three of these cases here. We'll start off with Q1. Q1 has a charge of plus 6 microcoulombs, so K is equal to 8.99 times 10 to the 9. What was it? Joules times meter squared per coulomb squared. I'm going to multiply by the first charge of plus 6.0 times 10 to the negative 6 coulombs, because that's what micro is. And we're going to divide that by the radial distance, and that's at 1.5 meters. Then we're going to add 8.99 times 10 to the 9 joules times meter squared over coulomb squared times negative 3.0 times 10 to the negative 6 coulombs. All right, as that vector is pointing this way. And we don't have to worry about, again, components or anything, because voltage is a scalar quantity. Okay, so the minus sign will take care of that part for us, because it was at negative 3 microcoulombs. This distance over here is still at 1.5 meters. That's nice and clean. The last one is 8.99 times 10 to the negative, positive. It is positive. Times to the positive 9 joules times meter squared per coulomb squared times negative 3.0 times 10 to the negative 6 coulombs. But this time around, you got to be careful. The radius is now at whatever 3 times root 3 over 2 is, measured in meters. Okay, so I think I had it on PowerPoint all cleaned up. In fact, I factored out what K was just to clean things up, and calculate away, and you'll get your answer. Okay, so in this case over here, there's a lot of potential energy. So if you end up putting just one electron into here, actually it won't be very much with one electron, because one electron is 1.6 times 10 to the negative 19, so it won't be much. But if you had a coulomb of electrons, which works out to an ampere of electrons, it's a lot, then the corresponding energy is insane. Okay, so that's the electric potential, at least at that point over there. And it will change depending upon where you measure this from. So you could measure it again from down here, and you can measure it again from over here. Okay. The second question is the fact that these are just charges in space, and they'll either attract towards each other or separate from each other. If you've ever played with ridiculously strong magnets before, you'll notice that they'll come together and they'll bash together and just smash apart. All right, and you probably won't see in the classroom, because when I brought in those super strong magnets, I tell the students to never put them close to each other, and guess what students do? They decide to place them close to each other, and they just smash into smithereens, right? Because that's how strong those super magnets are. Okay, so there's a lot of energy associated with charges, all right, and they can either attract towards each other or repel from each other, and that's what we're trying to figure out. Okay, how much energy there is in this particular scenario. Okay, all right, so we're trying to look for the electric potential energy, which the formula is equal to KQQ over R, and whether it's plus or minus, it's based upon whether it's going to be a force of attraction or repulsion. All right, so let's go and calculate through all of this. So it's the total energy of the entire system right now. So it's between the relationship of these guys, and these guys over here. Some of them may be positive and some of them may be negative, but we're looking for the sum of them all. Okay, and then we'll calculate it out and see what it is, and we'll figure out what it means afterwards. Okay, so we can just sub the numbers in. One thing that you'll notice here is that I did end up dropping the plus minus sign here, because one of the cool things about these scale calculations is that, remember that if they attract, then the only way for it to attract is if one is positive and the other one's negative. So if you sub it in, you're going to get a negative value. Right? And remember that for gravity, the gravitational potential energy, the U value was negative if they attract. Right? And if they're opposite charges like these two, or sorry, like charges like these negatives, then it will naturally create a positive answer. Okay, so we can just carefully sub everything in. All right, again, this will result in our negative sign, as they are opposite charges and they will attract, and like charges will repel anyways. Okay, so we can carefully sub everything in, calculate it away, and we'll get to an answer. And if you're super careful about it, you end up getting a negative answer here. And what does that negative answer mean? Well, that means that at the end of the day, these guys over here will inherently attract towards each other, or there will be an overall net value of attraction, right? Even though some may repel, overall they will come closer to each other. Okay, so if that's how much energy that it has in attracting towards each other at this distance over here, then you'll need just as much energy to break them apart. It's kind of like gravity and whatnot. All right, so if this is negative right over here, this is negative energy because they will attract. So if you want to break them free indefinitely, then the corresponding binding energy is the same quantity. All right, just the sign's different. So in other words, if you add in another 0.08 joules into the system, you could pry them apart and they won't attract towards each other anymore. Okay, here's another practice problem, and again, we need to use our previous skills in solving this part over here. Okay, so two protons coming from infinity come towards each other. Okay, and these are two positive charges. Now, with enough energy, they can smack together and bind and form into, I guess, helium, right? There's two hydrogen nuclei right now. They can bind together and form helium nuclei. I doubt that this will be traveling fast enough to create that, all right? Because here we're going to ask about, what's the closest that they'll get, even at these speeds over here. So one is traveling as fast as 2.3 times 10 to the 6 meters per second, and the other side is at 1.2 times 10 to the 6 meters per second. And keep in mind the speed of light is at 3 times 10 to the 8. So this ain't at the speed of light, right? Not that close to it, at least. Okay. Okay, so they're coming towards each other, and at some point, because they're like charges, eventually they'll pause before they ricochet off of each other. So if with enough speed, yes, they'll bind together, but this won't be fast enough for them to bind. Okay, so we're trying to figure out, well, how close will they get? Now, once they get to their closest point, you'll notice that they'll pause before they leave again. So in other words, they initially have kinetic energy, and when they're at this closest point, the kinetic energy should go to 0, because you have nothing but stored potential energy at that moment. Okay, and that's how you'd solve this problem over here. Okay, even before I state the givens, we know that total energy at the beginning is equal to the total energy at the end. How much energy do we have at the beginning? Well, it's equal to EK of object number 1 as it's moving, plus EK of object number 2 as it's moving towards each other. Okay, and at some point, I guess plus the U, but because it's infinitely far apart, that's going to go to 0. Okay. Why is that, you're wondering? Because of KQQ over R. If it's from infinite separation, then R is infinity, and anything divided by infinity will go to 0. That's all, because they're super far apart from each other. Okay, but when they are close to each other, whatever kinetic energy they have at the end goes to 0, because they paused as they are really close, and is stored in nothing more than just U energy. Okay, and that's a nutshell of how we're going to solve this problem. Now here are all our givens. Okay, again, the mass of the proton, it will be provided for you. All right, I don't expect you to memorize that. Same as the charge of a proton, which will be the same as the charge of an electron, if you recall. All right, except that you have a positive sign over here. Okay, and the other values are given to you in the givens. Okay, so with all of that stated, then we can just sub everything in, as I mentioned earlier. Go through all your number crunching and slowly solve for your UF. That's all. Okay, so when you've eventually your UF, and your UF will tell you the corresponding RF. What did I want to state over here? Oh, why is this positive over here? Remember that my UE is equal to plus minus KQQ over R. Okay. Again, if they attract to each other, just like for gravity, there'll be minus sign there in the integral. But if they're like charges, then it'll be a plus sign. Okay, so positive here since they are like charges. That's all I want to emphasize there. Okay, so you ever so carefully sub everything in, rearrange and solve for RF, and then you'll get to your answer. I think that's all I have to share with you. Yeah, that's it. Do your homework, answer all the questions, and I'll catch you in tomorrow's episode.